Alright, so welcome back to another session working on our project Croof. So since last time I did some small refactorings, fixed some bugs, but haven't really made any big changes on the language, so it still works the same. We give it an expression, it goes step by step, and it solves that expression using statements from stdlib, and then it gives us the result and also all the steps that it had to take to basically pattern match on the initial expression statements from our library, and then it gives the result that it managed to infer. So it's basically doing like an A-star search, so it's doing a breadth-first search on all the possible statements that it knows, and it tries to apply those statements on, for instance, 1 plus 1. So right now we have really basic math expressions, like you can think first grade, but usually in math, once you advance a bit more, you also get more complicated problems. Like for instance, you could have something like, oh, let x in natural numbers, x is greater than 0, and then you have to prove something like x plus 1 is greater than 0 or something. So you even have these, let's call them conditions, right? And that's exactly how our statements look. So if we look in stdlib, you can see that we have these kind of statements, and these statements are what we use in the solver to try and, how should we say it, like try to evaluate, but I mean it's not evaluating the expression, it's pattern matching the expression and trying to minimize its degree, if you will, because yeah, exactly, what we are trying to do is try to find the smallest possible expression that is equivalent to the first one, because the solver doesn't really know that, oh, we want to get a number in the end. Well, how can we tell it that? Well, by doing something like numbers have a degree of 0, operations have a degree of 1, so it's worse than a single number. So something like that, like telling it which kind of expression is the most interesting for us. So for instance, a single number would be the most interesting. But yeah, as you can see, we have these conditions, and then we have a then, and then we have another statement. So actually, interestingly enough, these are also called statements. So this for all, this negative 0 is greater than a, and then this is also a statement. So we have some statements imply some other statements, and here we can actually have multiple ones. But for now, we decided to keep only one on the right hand side for simplicity. But yeah, we have some statements imply some other statements. So for our addition, I would like to have something similar actually. Maybe even something like evaluate for all x in n. And then we can have 1 plus 1. Like, it doesn't matter that it's not related. I'm more interested in being able to add statements into the eval keyword, because right now it only parses a single expression, and then it evaluates it. But I would also like to include some initial statements, because maybe you have something like eval for all x in n, and then you have x plus x, and this is valid. The problem with it, however, is that my solution would be 2 times x. Like, this would be the ideal solution, right? Now we could try to prove this thing by using our I mean, it can also do proofs, but we don't really have a keyword for that yet, so we might maybe even think to reuse evaluate for proofs, but we'll see. So, but even then we could do this thing and then 0 is equal to, or like 0, and that's everything. But I would also like to not do that. So x plus x, the problem with it is that it has the same degree with 2 times x, so it might not want to solve it because it's gonna say, oh, but it's basically the same thing, why should I solve it? But anyway, it doesn't really matter. We could even have something like f of x is equal to x plus x, and then you want to solve f of 0 or f of 1, right? But I think this is good enough as an example. So in the end, you can even have letters in here because it doesn't care about, you know, numbers or something like that. It only cares that it can minimize the degree of this expression. So like right now the degree should be something like 1 for the plus 1 for each operand, so it's gonna be 3, I guess, if I remember correctly, right? And a single number would have a degree of 0. So, oh, actually, yeah, that's true, because I think a number has a degree of 0, so in total this should have a smaller degree. Maybe, I don't remember exactly. That should be in the AST. So if we have the degree, a number has a degree of 0, yeah, and the variable has 1 plus its arguments, but since it doesn't have arguments, yeah, so this should have a lower degree. Yeah, that's cool. So yeah, but right now we are not, so if we run this thing, it would say that expected an expression but found for all, right? That's because we don't parse this thing, right? We should parse statements, a comma, and then the expression in eval. So let's try to do that. So in the AST, we should have something like eval. Evaluations is just expression nodes, but as I said here, I would like to have something like a tuple, and we have a vec of statement nodes and expression node, right? So these are gonna be the evaluations. Okay, let's see where this thing is gonna break now. So here, that's the first case. So here we just change it, it's simple enough. Merging it works, evaluation. So here, what do we want to do is, well, maybe we want to just come up with something called evaluation node, just so we make it easier for us. So let's do that actually. So we are gonna have something like this. I'm gonna add comments myself, but right now it doesn't matter. So we're gonna have something called evaluation node, and it should have conditions, which is gonna be a vec of statement node, and for now it's gonna be an expression, but maybe in the future, as I said, maybe we'll have something different. So what do expression node? Maybe we'll have a statement, or maybe it's gonna be optional. We'll have to see. So it cannot have a default, obviously, that's fine. Okay. Evaluation node. Evaluation node. Okay, and here we want to display the evaluation node, but it doesn't have display, so let's implement display. Okay, how do we display it? Or something similar to this. I mean, display for implication node. I guess exactly that. Right? And the conclusion is just self-expression. Okay, I think that's fine. Maybe actually here we have a comma because that's how it's gonna look like. I don't really want to use the arrow there, so yeah, let's just see. Although it's gonna suck, actually, I think. Maybe we want to have a arrow in here. Just to make things easier to read. Right? So it's like, given that x is greater than 0, then solve x plus 1. Yeah, maybe it makes sense, I guess. It's gonna make it look prettier. So we have this eval, and then we show that. Okay, perfect. But right now, if we try to compile, we should get some errors. It should say that inside of the parser it doesn't work. Okay, perfect. So that would be the first step. Inside of the parser, when we are trying to, if we find an eval token, we should parse an eval now. But we don't have, evaluation. We don't have that yet. So let's push evaluation. So the closest thing to eval is actually implications. So let's copy paste this one and let's add it here. So it's going to be parse evaluation, and it's going to return evaluation node or parser error. Actually, st. Let me just add it to prelude just because. Okay, so this thing actually, well, I mean, haven't really done it well enough here, but whatever, you can pretend that it has commas in between and stuff. That's not really important. Expression. So here I guess it's only one expression for now. So we have an evaluation is basically a list of statements, at least one or none. So it's like doing star, but we have this extra arrow in here, and then we have an expression which should always be there for now. Maybe at some point we want to allow you to have expression or statement, and if you have a statement, then it's no longer evaluate this expression, but it's prove this statement. Okay, so we have that stuff, and at the end, so here we parse statements, right? Is conditions should be the same. If it's that, then So now this one is interesting because it's pretty hard. Because I would like to try and parse a statement, but if it fails, we want to fall back and try to parse an expression, and if it fails, then we error out. That's quite interesting. Because if we try to parse a statement and it fails because this part is missing, then we have this return result error, right? So it's not good. So what we want, something that we would like here is to clone our parser, try to parse. If it fails, we restore the parser and exit the loop by saying that we don't have any conditions. And if it works, then it works. Then it's fine. But that's only for the first case. So let's say let mutable clone is self.clone, I guess. Okay, so struct parser, let's make it derive clone. No, clone should be enough. So we clone this thing, right? Then we should say something like if let okay clone, we'll have something here is equal to clone dot parse statement. So if we have this thing, we should also have a mutable statements. Else we don't really care actually. And maybe is conditions let is conditions is equal to this thing. So on this case we have a true, in this case we have a false. All right. But I would also say that if it worked, we want statements dot push statement. And I would also like to do the loop, kind of. But at this point we know that we have statements. So I would have to parse this thing and then go again. But I guess the easiest way to do it would be loop. Wait. loop we push the step. Okay, anyway, let's just try to implement it, and then we'll figure out how we do it. So we'll do that. Do we really have anything else? So if we find a then token, then we should stop. If we find a comma, then we should do the loop. If we find anything else, it's impossible. It's kind of an error if we find anything else. Actually, I mean, okay, fine. Let's do something else. So let's do something like if is conditions. We run this loop, and even though we have to parse the statement again, is like a bit inefficient. It's fine. It is what it is. So here we look basically into the future of the parser. We try to read the statement. If it works, then it means we have some conditions. Then we have to parse them. If it's not, then we can skip this entire step, right? And if we have some conditions, then we have to do this kind of stuff. But here, as I said, it should be an error. It's like impossible to find this. So we parse statement. We do that. Yeah, here it should be an error. Return. Do I have something like that? Like you should have then. That's what I mean. Expected then or comma. But found a token. Okay. That's what I think about this. Then if we don't have conditions, or I guess if we have conditions, or even regardless if we have conditions or not, I don't really care. So we have the conditions, then we can have only one conclusion, which is going to be an expression. So let expression is equal to self dot parse expression, and that can also fail. So we do evaluation node, new conditions, and, or I guess, yeah, expression st input evaluation node pub fn new, and expression is expression node. It returns self, and we do that. Okay, so now we create our evaluation node. That's pretty cool. So what should we do next? Let's see what other errors we get. We should get some errors in parser. In type checker it makes sense. It's yeah, it's in only in type checker. Perfect. So let's go into type checker. So here it's going to be check expression that's being used, but I want to see where it fails. So check expression, it should be check evaluation. All right. check evaluation. And no, hash map is going to be similar to check implication. So let's copy paste it. Check implication. We can go below the define. Check evaluation. We are going to have evaluation node. Perfect. And we can get a vec of type check errors. We have symbols. So this is going to be evaluation conditions. We check the statements, and at the end we have to do errors.extend serve.check expression evaluation.expression, and we give it symbols. What? Expected immutable. I mean, yeah, sure. Mutable. What do you want? String type node. It's fine. Option. How did it work before? It's yeah, okay, like this. And then here this thing returns an option with a type, and or I guess an option with a type or list of errors. So we are interested in one, so the errors. We don't really care about the type. The type is gonna be the reason why we send here immutable is because we modify the expression to change its type. Okay, nice. So let's see, I guess it should also have some errors in the main or in the solver. So one of them is display solution, and solver solve. It expected expression out, but it found evaluation out. So we want to change that. Main, display solution, I don't really care. So solve, it should actually take in evaluation node. Evaluation, and for now let's just pretend that we have evaluation.expression so that it works. Okay, whatever. And trait. Evaluation node. Evaluation. Okay, fair enough. So that's and we give it just the expression for now. We'll see how we also give it the full evaluation, but I don't know, I think it's fine. And display solution, let's call this evaluation. And this can be evaluation. It's fine. So if we build this thing, it should work. So parser 402, we have this thing which, I mean, it's kind of useless, but oh, actually we can just say is okay, right? Is okay. because we don't really care about anything else for the moment. So yeah, so this should 5-1 in 0-1 Croof. Because I said that we'll change it, oops, so that we use an arrow in here. Okay, so it's gonna do 1 plus 1 is equal to 2 because it is what it is. Right now we ignore the conditions, but let's try to not ignore the conditions. And then no solution was found for x plus x. Fair enough. I guess we don't have something like, so if we go to std lib, we don't really have a way so for multiplication, for instance, we don't really have a way to tell it on how to like this would be pretty hard to figure out. So we can just come up with something. So for a, and let's say a plus a is equal to 2 times a. Let's see if it finds it. I guess it's not happy with the result of 2 plus a, and it tries to find something else, and it gets stuck. And the main reason why is because in solver we have the degree is equal to 0. So let's say degree is less than 2 maybe, just to see if it finds a solution for the last one, right? But yeah, there's the problem. These are less than 2, so somehow it should be like the minimum possible, but it's hard to use a star like that. So yeah, anyway, so we're this one is kind of hard. Then solver. So here I wouldn't send the evaluation directly. I'd say how should we solve that? Like we should prove all the things and then we should solve that. So that's how I think I want to do it. I think we have to iterate all the statements, prove them, and then evaluate the expression. Or I guess solve a star. But that's also kind of annoying. Main reason is proof statement. Is that those initial conditions can give us some extra info, and I like that's the goal with those statements, not really to prove them, but to give us some extra info. Like somehow add them into the context. Because what if we define a function? So let's just pretend we do something like that. What if we have for all f is a function then f of x is equal to x, then solve f of 0. I mean, we can still keep that just for the memes. Binding x is not defined. Wait, do I really define it usually for all x in n? I guess I have to define it. And then it says no solution was found, right? What if we keep only this solver substitute? No, that's maybe in the matcher. Substitute helper. I do something like 4s in substitutions, print ln s. Expression node equal 0. Okay. So I didn't even try anything, right? That's what I am seeing. Interesting. Evaluation.expression f of 0. Okay, so it's gonna go into solve a star. Then we have these things, push, substitutions clone, self substitutions. So it uses the implications. It uses the implications to run the matcher substitute. Matcher substitute takes in our expression and an implication. Substitute helper needs the conclusion of that. And it does this, you need to prove the conditions. Okay. Interesting. So substitute implication. Maybe it's kind of scuffed. But yeah, we need this thing like conclude. We need a conclusion for finding the substitutions. That's kind of rough. Expression create mapping. because this implication, like the conclusion, if you think about it, could be this f of x is equal to x. This could be the conclusion, but it's not really of like an implication, right? So it's kind of annoying. Like it could use this thing f of x is equal to x to make the substitutions, but how do you know that this is the one you have to use? You have to try each one. We would have to try each one of these to try and make the substitution. So that's kind of the point here. So this one with substitute helper would actually work better if it got as an argument, maybe, I don't know, what do we use this thing for? Implication. We use it as an argument, that's fine. Then we map over the conditions. If it's whatever, we apply the mapping on the conditions. For some reason. And so we just apply the mapping. Yeah, we apply the mapping here, and then we push the substituted thing and the conditions to prove them later. That's how it works. So I would say maybe it would be cooler if this function got as an argument the conditions and the conclusion. So what I'm saying is conditions as vec statements and the conclusion as a single statement, right? So for instance, here we basically handle this thing, right? Because right now this one is decoupled somehow. So this should take in conditions and conclusion. We basically change this function. So let's actually change it. Substitute takes in this stuff. So here it's conditions and conclusion. Right. So substitute works. Substitute here, it's conditions and conclusion. Here as well. Here as well. Statement is just the conclusion. Here we have just the conditions. Conclusion. We do some stuff and then we have that. Perfect. So now it works by using conditions and conclusion. It doesn't really carry implication. You can give it a list of statements and a single statement, that's the conclusion. So that's how substitute should actually work. So now inside of the solver we should have some errors. So here, when we generate the substitutions for A star, so here we generated the neighbors. We should say conditions, obviously with the reference and implication dot conclusion, maybe also with that. Oh, conclusion 0. we still just note, we still assume one conclusion node. But as you might see in a second, so here we get in a single expression. Let's change it to get in the evaluation. Okay, it's here. So this takes in the evaluation. That's cool. So solve A star. Solve A star, let's change it to take evaluation node. So here it's gonna break, it's gonna want evaluation. Oops. Solve A star. Node is relation. Maybe maybe we still want to do expression and conditions or something. Vec of statements, for instance. Right? And for a proof statement, actually, this one takes a list of statements. Proof. Not sure. So here what it does is it maps the conditions and it appends the expression, that's the final expression, and the conditions or statements actually that we need to prove. I mean that's different because we need to prove each statement kind of. So that's kind of meh, because here we need to prove this statement. For now, let's just give it an empty vec as the first argument because I'm not sure. Right. What? Whatever. It wants that. So that's maybe what I think. And here evaluation dot conditions. We give it the conditions. Right here they are not used. But instead of substitutions, we should use them. So substitutions is called here, and that's the only place. So this generates the neighbors. This one generates the neighbors. It returns the proof step. So what you have to prove? Maybe we can address this one first. So here we index 0, but what we should do instead is for conclusion in implication dot conclusion, we should generate a substitution for each one, I think, or at least we could generate a a substitution for each one. So I think that's what we have to do. So we solve that issue actually. Maybe, I'm not sure. We'll have to see. That's one step. And the other one is to try and use the conditions somehow here, because they are going to be needed when we generate the neighbors. So maybe we pass that to here, conditions. I guess we have to pass it there. Clearly we have an expression. We have some conditions that we can apply. So those things should be used during substitution to generate all the neighbors. It makes sense. So we get the conditions. Implication node. We don't really have implications. But here we have a list of statements and only one statement. So I will do something like for condition in conditions. We should do something similar to this. But we should say self-matcher substitute expression. Conditions is going to be conditions, and the conclusion is going to be the condition. Monument. Oh, paper. And here we say, okay, prove the steps that we got. Hopefully we don't get any. Then we have the expression that was substituted, the implication that we don't have for now, so we have to create an implication. I don't fucking know how, but we have to think about that. And then the steps. So implication node. Do we have a new? We have a new. Oh, so it's just the conditions and conclusions. So I think we don't have any conditions, and the conclusion is going to be just what we used there, I guess. So it's going to be an empty vec and the vec with a condition. Dot clone, whatever. So let's try to see this one. Okay, let's try to run it, and whoops, match, implement the mapping. So we have hit a to-do. Matcher at 69. Oh, nice, 69. So if the conclusion is a quantifier, I mean, if the conclusion is a quantifier, here it kind of depends, but let's do nothing for let's do nothing for now. So hash map new. Wait, what? This is the mapping. I'm not sure to do. Back. So substitute. Okay, for s in substitutions, println s. What's on s? Let's do 0. Nothing? The fuck? Not even from here? Let me just see the implementation. Fuck. That's kind of... Wow. Rust being rust. F of x is equal to x. Right, that's like enough. But wait, that means we have substitutions. Wait, what the fuck? Help. Like, we literally have something, right? I guess the steps is wrong or something. Print ln. And it fails to prove the steps or something. Yeah, for s in step. But why do we have steps though? That's the question. For all step f of 0 is equal to 0. What the fuck? Prove steps, but which one does fail? So prove statement. I mean, if it's a quantifier, it's okay. So clearly it failed on f of 0 is equal to 0. But it's weird. Why does it even... So conditions, I guess maybe we want to do conditions without this condition. Conditions without the condition. But it's also weird because we kind of assume that the conditions are true. What do we use conditions for? Okay, let's see. For substitution. And then here we map them. Quantify relation. We try to apply the mapping on them. And then prove them. Okay, I think maybe we don't want to send them in here. Wait, what? Oh. Maybe we just don't want to send them, I guess. Measurement E3. So if we get a quantifier as the conclusion, substituted is an option. I guess none, because reasons. Let me just do back. I don't know, maybe we want to do something with quantifiers, but we actually got it. So we have this expression, which is for all x, for all n, for all f, sorry, we have f of x is equal to x, compute f of 0, and then it actually computes it. Fucking legend. Let's remove the prints. So we actually got it. That's pretty cool. Let me just copy paste that and let's add it here. Wait. Yeah, that's fine. So it can still wait, where do I have some, oh, where do I have some prints? Oh, here. Okay, just remove the extra prints and now it should look good as it did before. So we are actually able to cover all the cases basically. Maybe there are some, you know, hacks I had to do like with those quantifiers, but yeah, this is actually pretty cool. Being able to solve expressions like this. So yeah, let's just see if everything still works, hopefully. 04. Fibonacci, it's still a bit slow, but it should work. I mean, obviously they will work because they are not using the new feature, but it's still fun to test it. Nix. Let's run the checker. Okay, cargo run or cargo test. Not sure if, okay, so everything works, and we also are able to solve complex expression. I mean, I'm calling them complex expression because they are, you know, they are using multiple statements, and then the expression that we want to solve. So that's pretty cool. And yeah, I guess that's it for today. I'll have to, you know, make the commit, look at what I changed, see if there are any bugs in those to-dos that I left, and yeah, maybe we'll see next time with some more Croof, maybe something else, I'm not sure. If I find any other interesting ideas that we can explore with Croof, maybe doing some more complex stuff, we can try to figure that one out. If not, then yeah, I mean, it's still pretty interesting to work with this language. So yeah, let's see in the next one. So see you.